This is a series of 3 videos where we want to talk about how to use definite integration to find the volume. Now, but not any volume, they must be what we call volume of revolution. They are made by revolving an area, a region around an axis so that you have a volume of revolution. So now the axis is important. Say on the left hand side and right hand side, you can see here they are both the same region. I marked them in green. But if on the left hand side I revolve about the y-axis, alright, it's called revolve about y-axis. Whereas on the right hand side, I try to revolve it about the x-axis. Revolve about x-axis. Now the shape, the object that create in this way, they will be different. If you turn this green region around the y-axis, then you will have something like this. You will have kind of like the shape of a conical flask, something like that, right, with circular bottom at the top. That is what you get when you rotate it across about the y-axis. On the other hand, if you rotate it about the x-axis, you will get something very different. It looks like something like a circular disc, right? But then in the middle of the circular disc, there is kind of like a part that comes out from the disc, alright? So not just the volume, even the shape is entirely different if you choose a different axis of rotation. So you have to pay particular attention on the axis of rotation, otherwise you'll get the wrong volume, alright? So now you can see there are two kinds of rotation. You can rotate about the y-axis or you can rotate about the x-axis. Let's see how do we do the calculation. If you rotate about the y-axis, say for example, and the curve is like this, okay? If you rotate about the y-axis, you will have an object kind of like this, right? It will be like a flask, something like this, alright? Now if you slice them up one by one, each element will be a circular disc. For that circular disc, the surface area will be pi x squared, where x is the radius, right? Each of this becomes something like this, right? So what is x is now the radius, but the width of the disc, the thickness of the disc is dy. Alright, so each of this disc, the area is pi x squared dy. Now, as we mentioned in the chapter on area, the integration is to add them up. So the total volume is to add up the individual volume of this disc. Pi x squared is the cross-section area, and dy is the thickness. We do it from the smallest y, say y equals to p, alright, all the way up to the highest y. So maybe the highest y is up here, right? To y equals to q. So we put the boundary y is p to y is q. So that would be the volume if we do a revolution, a rotation about the y-axis. Now on the other hand, we can do the revolution about the x-axis. So it goes to something like this, right? If we have the curve and then the curve is like this, alright, we do the rotation about the x-axis. So like this part is rotate about the x-axis. So we will have something like this, right? Kind of, we will have something like this. So if you cut up the volume, once again you slice it up, you will have the element of each is a disc. Each of this rectangular, after the revolution, becomes a disc, alright? And the height of the disc becomes the radius, and that is y, right? Y is the height of this rectangular block. And then the thickness of this disc is now dx, alright? So we do the integration from the smallest x, say x is a, all the way to the largest x, say x is b. So each of this disc, the area is pi y squared dx. And the total volume will therefore be pi y squared dx will integrate from x equals to a to x equals to b, right? Now it's different from area. You have no choice. In area, you can choose whether to do it vertical slicing or horizontal slicing. But in volume, you do not have this liberty. You have to follow the axis of revolution. If it is revolving about the y-axis, you have to do this, pi x squared dy. On the other hand, if it revolves about the x-axis, you have to do this, pi y squared dx. You have no choice. All right. So let's take a look at some of the example on how do we apply this skill to some of the objects that we see frequently. Say the volume of a cone. All right. Now in junior form, you know that it is 1 over 3 pi r squared h. But where did that 1 over 3 come from? All right. It was a mystery. They just told you that it is 1 over 3. But now we have a chance to redeem ourselves, right, and see why is it 1 over 3. Alright, so we have this part, right? The region under the red curve will be like this. We're going to revolve it around the x-axis, the y-axis, sorry, right? So suppose this is r, this is h, alright? So now what is the equation of that straight line? That equation of straight line, we can use the intercept form, or you can use two-point form, right? But for efficiency, I adopted the intercept form. It might not be very familiar with you, but it's okay. You can use two-point form. But anyway, the straight line is like this. All right. So for each of this element, is turning out into a disk. All right. The outer rim of the disk should be in red. All right. The length of the radius should be this x, and the thickness is dy. All right. We start from this smallest y equals to 0 to y equals to h. Alright, so the volume of the cone goes like this. After the revolution, it is a cone, right? The base radius will be r and the height will be h. And that volume will be the integration. We do the pi x squared. Pi x squared is the surface area. Alright, and then dy. Y starts from 0 to h. Alright. That is how we use the volume of revolution to get the volume of the cone. All right. So now let's see what x squared is. X squared is r squared 1 minus y over h. Take the square. All right. From here we can do the conversion. We can convert it into x equals to r 1 minus y over h. Am I right? It's a simple change of subject. Then you integrate from 0 to h. Alright, so that is pi r squared. And then, I can do the substitution. I can substitute. Let's see, I can substitute u equals to 1 minus y over h. Alright, so then we have du will be minus 1 over h dy. Or shall I say, dy is minus h du. Alright, this is dy. And then that 1 minus y over h becomes u squared. Alright, it becomes u squared. So finally, how about the boundaries? The boundaries when y is 0, when y is h, what should be u? Alright, when y is 0, u is 1. Alright, when y is h, u is 0. So we have when y is 0, u is 1. When y is h, u is 0. So this is it. So you use the minus sign to swap the boundary. So we have pi r squared h from 0 to 1, u squared du. Alright, and that is where the 1 over 3 comes from. Alright, and that becomes pi r squared h 1/3 u cubed from 0 to 1. So the final answer goes to our familiar 1 over 3 pi r squared h. And that is how we find the volume of the cone using integration. How we find the volume of the cone using integration. Alright. Right, notice when you do the revolution about the y-axis, it must be pi x squared dy. Right? Each element is a disk. The radius of this is x, and the width, the thickness is dy. So each small disk, the area is pi x squared dy. For all of them add up together, we use integration from the smallest y to the largest y. All right, and then what we do after this one is to replace x with the corresponding y and finish the integration. So that's how we do it. All right. All right. The last example in this part is to find once again a common object, the sphere. All right. But let's do a semicircle. Right. So the circle goes like x squared and y squared equals to r squared. That is the circle. It's r squared. All right. So we want to find the volume of a hemisphere. Sorry, hemisphere. Previously, we want to find the volume of a circular cone. All right. So let's do the revolution about the x-axis. Then we have a hemisphere like this. All right. Now each element is this one. All right. Each one rotates into a circular disc. A circular disc. The radius of disc was y. All right. The thickness of the disc is dx. So each of these small discs, the area is, the volume is pi y squared dx. All right. We do the integration from the smallest x is 0, all the way to the largest x is r. Right. So it's from 0 to r. That is the volume of a hemisphere. So how do you change y squared into x? We can change it into r squared minus x squared from the original equation. All right. Because x squared and y squared is r squared, so y squared is r squared minus x squared from 0 to r. So this integration, in fact, is easier than the previous one. R is a constant, so it's just r squared x. Minus x squared will be 1/3 x cubed from r to 0. All right. Oh, sorry, I should use the capital R here. Sorry, I should use the small r here, right? Sorry about that. It should be the small r. All right. So that would be r cubed minus 1/3 r cubed. So the answer is 2 pi over 3 r cubed. That is for the hemisphere. So therefore, for the whole sphere, the volume will be twice of the hemisphere. All right. So that goes to 4 over 3 pi r cubed. So that's why the 4 over 3 comes from. All right. So this is the end of the part 1.